All right, in this module, we're going to talk about the phase rule or the Gibbs phase rule. All right, so this is a very powerful rule for phase diagrams that tells us that only a certain number of phases can exist at equilibrium, and it gives us that number. And so that is governed by thermodynamics. And so this is actually a relationship that can be derived somewhat simply. You may do this in thermodynamics, but we're going to leave that up to a different class. And we're just going to kind of go over the implications of the Gibbs phase rule. And so this is the Gibbs phase rule, which is stated as P plus F equals C plus N. So again, very simple rule. And what all this means is we have P, capital P, is equal to the number of phases present. F is equal to the number of degrees of freedom, and I'll talk about this term in a bit. And then C is the number of components in the system, and N is the number of non-compositional variables in the system. And I'll mention this to an extent as well. So for a lot of the binary diagrams that we've been looking at, we're kind of assuming constant pressure. So if we think about the non-compositional variables in that system, then, well, composition isn't a variable because it's in the name, right? Pressure is held constant in most of these systems. So T is the only one left. So in those systems, like the one we have over here, where we have composition versus temperature, the only variable left is T. And so N can be, N will be will be 1. If you have a system like the water phase diagram that I showed you, then pressure would still be a variable, and temperature would be a variable. And so therefore N will be equal to 2. So typically, if you're shown a phase diagram, you can infer what the number of non-compositional variables is by the axes, right? So temperature, composition, that means pressure. If there's no other indication, pressure is held constant. And so then temperature is your only variable, so N equal 1. If you see pressure on this diagram, then obviously you would have N equal 2. So components are what we've talked about before, right? These are basically the x-axis, right? So copper and silver in this case, we have 2 components. It's a binary diagram, right? So the name often tells you the number of components. So for a binary, you're going to have C equal to 2. For a water phase diagram, right, there's only one component, water. And so that is 1. And then we're kind of left with the degrees of freedom. And we're going to talk about this in a second. So degrees of freedom is the number of externally controlled variables. And I like to kind of work through this with some examples. So if we have a simple diagram, much like the water phase diagram, right, where we have pressure and temperature, and then we have solid, liquid, and gas. If we say we're at a given point A, and we want to externally control variables, right? So the variables that we can tune are pressure and temperature, right, in this case. So if I move from A to a point A prime, that means that I'm changing the temperature. So I'm going over here to the right, and I'm changing pressure slightly by going down. So I've changed both temperature and pressure. So in this case, in this phase region, I'm allowed to change both temperature and pressure, externally controlled variables, and I'm allowed to control 2 of them without moving into a different phase region, like the 2-phase region here, like the liquid, like alpha. So this, in this scenario, I would have, in this phase region of gas, I would have 2 degrees of freedom. And if you put a point in the liquid, or if you put a point in the solid, and you talk about that degrees of freedom, it would be the same. You're allowed to move both temperature and pressure and still have pure solid or have pure liquid. So if we look at a different scenario now, where we now have two phases. So I'm at point B. So at point B, I'm in equilibrium between solid and gas, so sort of sublimation, if you want to think about it there. And if I want to still have two phases in equilibrium, so I have to basically be on this line, I can move one variable, right? I can move temperature. I can increase the temperature to the left, or sorry, to the right, but that means I also have to move pressure by a certain amount to be at B prime. I can move pressure by going up, but then I have to move temperature a fixed amount to maintain that line. So I can only move one independently controlled variable at a time to maintain the equilibrium that I have. So I can either move temperature or pressure, and then the other one is fixed to get to a different position on this line. And so in this scenario, on this two-phase equilibrium line, this boundary, then my degrees of freedom is 1, because I can only move temperature or pressure. So the last scenario, let's say we're at the triple point, point O. This is where solid, liquid, and gas are in equilibrium. So here, I can't move temperature or pressure and still be at that point, right? Because it's a point. We know what a point is, right? We can't move and still be on that point. So neither of those variables can be controlled. So I have 0 degrees of freedom. So I can't move anywhere. So that's what so basically through these examples, that's what a degree of freedom means, is you're allowed to move the variables, the independently or externally controlled variables. So I can, increase the temperature of a furnace. I can adjust the pressure in a chamber, right? Those are my variables. And in this case, I can't move either one of them. And so that's 0. All right. So putting together those scenarios with the different degrees of freedom and looking at the number of components I can have. So we just looked at the one component system, and we looked at scenarios where we had 1, 2, or 3 phases. We saw that the degrees of freedom was 2, 1, and 0. So we can go through the same exercise, but we won't here right now, of the number of components being 2, and looking at when we have 1, 2, 3, or even 4 phases, and we see the variation in degrees of freedom. And that allows us to formulate the Gibbs phase rule, like we just saw before and you've seen in the previous slides. So this, again, the power of this expression is that it allows us to determine the number of phases possible in a scenario, and that is tied to the degrees of freedom. And so we can look at a specific scenario in a 1, 2, 3, 4, 5 component system and look at the number of phases that are possible connected to this term degrees of freedom. So in the next module, we'll go through an example of this type of question.